Hello and welcome to The Complete History of Science, Series 7, Episode 1, The Lodestone, the Compass, and the Magnetic Earth. The earliest reference to magnetism in Western sources comes from Thales of Miletus, a Greek philosopher active in the 6th century BC. Thales noted that a particular type of stone, called the lodestone, pulled iron towards itself. He explained that lodestones possessed a soul which attracted iron. For Thales and other early philosophers, movement was connected to life, and so the pull of the lodestone demonstrated that it was in some way living. Over the succeeding centuries, Greek philosophy evolved. Plato, writing 200 years later, described magnetism as caused by the motion of invisible particles which push each other around. His account was only brief, and he was primarily using magnetism as an analogy to discuss the transfer of ideas. Aristotle, Plato's student, described the lodestone and Thales' work, but omitted his own detailed account. In general, magnetism was problematic for Greek philosophers, as they disliked the notion of action at a distance. They believed that for a force to act, there must be some direct contact between objects. Perhaps the group of ancient philosophers who devoted most attention to magnetism were the atomists. Their fundamental belief was that everything consisted of tiny indivisible atoms which moved around in a vacuum. According to the atomists, all phenomena could be explained in terms of these atoms, and in this context they developed various theories to explain the action of the lodestone on iron. One theory was that the lodestone pushed away particles of air, causing iron to move into the vacuum created. Another was that attraction was caused by small hook particles, which emanated from the lodestone and pulled the iron towards it. Naturally, there were many issues with these explanations. The ancient Greeks eschewed practical knowledge, meaning they lacked familiarity with the details of magnetic phenomena. They were unaware, for example, of magnetic repulsion. Consequently, their theories were developed post hoc, from just a few observations of lodestone and iron. Fortunately, while developments in Europe stagnated, new discoveries were made in the East. In the 1st century BC, a classical Chinese text, Lung Heng, includes a strange description of what was called a southwards-facing spoon. It had been discovered that when a spoon carved from lodestone was thrown to the ground, the spoon tended to align itself with the direction of the South Pole. This is the first known description of the magnetic compass effect, though it would be centuries before it was utilized for navigation. Instead, it was used as a method for fortune-telling. Diviners' boards from this period survive, with engravings of Ursa Major, a constellation in the southern sky, indicating a supernatural connection to the South Pole. From these mystical foundations, the compass evolved into a practical tool. It was found that by suspending the lodestone on a silk thread, or alternatively on water, the lodestone could move more easily. 11th century artisans made further advances by replacing the lodestone with permanently magnetized iron. During the Song dynasty, the polymath Shen Kuo compiled a great encyclopedia of Chinese science and technology. In it, he described how rubbing an iron needle repeatedly along a lodestone caused it to gain the south-seeking ability. This was advantageous, as iron was far more common than lodestone and could be readily fashioned into light needles. By the late first millennium, the Chinese were regularly using compasses for navigation during dark or cloudy weather. Sailors favoured wet compasses, with the lodestone or iron floating in vessels of water. These proved reliable enough that they were only supplanted by dry-pivoted compasses in the 16th century. The Chinese geographer Zhao Rukou noted that sailors trusted their lives to these instruments. He wrote, "At times of storm and darkness, the pilots of the merchant ships travel trusting to the compass alone. They dare not make the slightest error, since the lives of all those on the ship depend upon it. The water of the ocean is shallow near islands and reefs. If a reef is struck, the whole ship may well be lost. Your life depends entirely on the compass needle, and if a small mistake is made, you will be buried in the body of a shark." The remarkable accuracy of Chinese instruments was not only a practical advantage, but also led to the next great discovery in the study of magnetism. In his encyclopedia, Shen Kuo noted that the compass needle doesn't quite point directly south. This is known as magnetic declination and reflects the fact that magnetic south does not correspond to true south. Instead, Shen Kuo took precise measurements of declination and found that the needle pointed 15 degrees east from true south. The precision of this measurement reflects the fact that the Chinese were by far the most sophisticated instrument makers in the world at the time. In Europe, it was another century before the first reference to the compass appeared. In 1190, Alexander Neckham, abbot of Cirencester, mentions that the compass was used by sailors. The description he gives is of a dry pivoted design, though the account is somewhat garbled, and it's likely he had no first-hand experience himself. Scholars have argued that the sudden appearance of the compass in Europe in relatively advanced form implies that it came from the East. This argument is compelling, though there's little evidence mapping its transmission. In Europe, during the Middle Ages, writers were not particularly interested in craftsmanship or instrument design, and the compass was of little concern. An exception to this is the work of Peter Peregrinus. Born in Picardy around 1240, Peregrinus was one of the most important scientific figures of the period. He was a mathematician and philosopher who, unlike his contemporaries, didn't scorn practical knowledge. Likely, he trained at a scholastic university, but also worked for some time as a military engineer for the French army. Roger Bacon, slightly younger than Peter, became a great admirer and wrote that it was impossible to write a useful or correct treatise in experimental philosophy without mentioning this man. We know, however, of only a single treatise by Peter, the Epistola de Magnete. Written in 1269 as a letter to a noble friend in Picardy, Peter supposedly wrote this whole work while laying siege to the town of Lucera in northern Italy. But clearly, the work represents several years of careful investigations. The treatise is remarkable, as Peter far surpassed the ancient Greeks in his knowledge of magnetic phenomena. He found that magnets contained two opposite poles, and realized that they could also repel. Based on this idea, he formulated a theory of attraction and repulsion, whereby opposite poles attracted and like poles repelled. Peter also described a method for finding the location of the poles. In his investigations, he used magnetic lodestones carved into spheres. These spherical magnets became known as terella. To find the poles of the terella, Peter lay a small iron needle across the surface of the magnet and traced the paths of these needles to find the location where they met. At the poles, he found the iron needles stood vertically erect. He also noted that poles were always on opposite sides of the sphere, and remarked that attraction was strongest in these regions. Peter then asked an obvious question. What happens to these poles if the magnet is broken in two? In his subsequent experiments, he found that the fragments would have two new poles, effectively leaving him with two new magnets. In the second half of the letter, Peter describes in detail compasses used at the time. He knew of both wet and dry versions, and describes graduated markings with a resolution of a single degree. These compasses were likely common designs used at the time, rather than Peter's own inventions. More importantly, Peter examined contemporary explanations for why the compass aligned north. During the period, there were two main theories. The first was that the needle was attracted to the North Star. Peter rejected this theory on the basis that the compass does not in fact point towards the North Star directly. The North Star is actually a few degrees away from the celestial North Pole, and over the course of the day rotates on a short orbit around the celestial North Pole. If the magnet were truly attracted to the North Star, Peter reasoned that a similar motion should be observed in the compass needle. The other popular theory was that there was a large mountain of magnetized iron or lodestone somewhere in the north, which attracted all compass needles towards it. This theory was very persistent, and though Peter rejected this idea too, he lacked the evidence to directly refute it. Peter Peregrinus died in the late 13th century, and in the period that followed, there were few developments in our understanding of magnetism. Use of the compass, however, proliferated, and by the Renaissance, it became a staple tool of European navigators. They increasingly used dry compasses over wet, and new designs incorporated protective housing with a more stable needle point. This allowed the compass to be used in rough conditions far out at sea. For the first time, sailors attempted long ocean voyages. By the 16th century, a class of specialized artisans emerged who created ever more accurate instruments. One former sailor, Robert Norman, became a compass maker, and in 1581 published a text called The New Attractive. In the book, Norman lays out everything that was known about the compass at the time, as well as new discoveries he'd made in his own workshop. During those days, there was much myth surrounding the compass, but Norman, approaching his subject with scientific rigour, made great advances separating fact from fiction. In his own words, Norman promised to ground his arguments only upon experience, reason, and demonstration. He makes good on this promise throughout The New Attractive, and brings to bear his own expertise from his time as a navigator. For example, he agrees with Peter that the compass needle does not point north due to a magnetic mountain, but unlike Peter, Norman has evidence to support his assertion. He says that during his career at sea, it was well known there were large iron deposits near the island of Elba. Sailors passing Elba, though, did not witness any deflection of the needle, demonstrating that geographical features were not strong enough to affect the direction of the compass. Norman does not attempt to offer an alternative explanation, preferring to report the facts without speculation. The New Attractive's purpose was to help solve practical issues faced by navigators. Chief amongst them was the problem of magnetic declination. Declination was well known in Europe at this time. A compass made by the astronomer Georg Feuerbach in 1451 includes a mark indicating the point where true north deviated from magnetic north. Unfortunately, this was not a complete solution to the problem. It had become clear from sea voyages that the degree of deviation changed depending on location. Columbus, in his journeys to the West Indies, set values for declination while in port and simply stuck to these values for each leg of the trip. This may have been good enough, but was problematic for planners and navigators who hoped to optimize their voyages. Confusion reigned during the 16th century on the nature of declination and how to deal with it. Some believed that declination must vary in a predictable fashion. For example, the explorer João de Lisboa believed that at the Azores, true north and magnetic north pointed in the same direction, and would then vary linearly east or west of this point. There was even the suggestion that declination might solve the longitude problem. The idea was that if declination varied predictably as one travelled east or west, it might be possible to infer longitude at sea. The English seaman, George Best, was far more cynical, doubting that declination varied predictably. Instead, he suggested that the only way to deal with declination was to keep records of observations from around the globe. Others began to doubt that declination even existed. Spanish navigator Pedro de Medina thought it was due to deposits of iron or lodestone, causing the compass needle to deviate from true north. Norman, drawing on his experience at sea, as well as his years making compasses, confirmed that magnetic declination was a real phenomena. However, his research dashed hopes that declination could solve the longitude problem. The issue was that though declination varied, the same degree of declination could be found at different points. As a practical solution, Norman agreed with Best and suggested that careful measurements of declination should be made in many different locations. Norman himself made a measurement of declination in London, reporting a value of 11 degrees and 15 minutes to the east of true north. By Norman's time, instrument makers like him had refined the compass to achieve unprecedented accuracy. In his workshop, Norman's meticulous experimentation revealed an effect that even Chinese master craftsmen had overlooked. Norman found that compass needles, which should have balanced on a pivot naturally, inclined downwards. At first, he thought there must be some mistake and cut his needle shorter, but found the problem persisted. He soon realized that magnetized needles were consistently pulled downwards, a phenomena known as magnetic dip, or more formally, magnetic inclination. Inclination had been noted before by Jörg Hartmann, a vicar in Nuremberg, but his observation was hidden in an unpublished letter. Norman almost certainly discovered the effect independently and investigated it more carefully. He constructed an instrument which allowed the needle to pivot in the vertical rather than horizontal plane. In London, Norman found that the compass needle dipped 71 degrees below the horizontal. His hypothesis was that there was a point, called the point attractive, somewhere within the Earth's interior, which attracted the needle. This implied that inclination would vary depending on location, and he hoped that in the future, sailors in distant parts of the world would make their own measurements. Beyond this, Norman did not speculate on the meaning of magnetic inclination, or why the compass should be drawn to this point. As a craftsman, Norman did not see it as his place to explain these phenomena, and as a religious man, he attributed the workings of the world to God's providence. Nevertheless, in the late 16th century, the work of men like Norman began to have a wider influence. The university-educated, who in previous generations had shunned practical knowledge, began to appreciate its value. William Gilbert was one of these men. Whereas Norman's education happened on the high seas, Gilbert studied at Cambridge, where he completed a medical degree. This background introduced Gilbert to the work of the Greek philosophers, in particular Aristotle, whose thought still formed the basis of all university education. Like many of his contemporaries, though, Gilbert rejected knowledge derived from books, instead preferring to investigate nature for himself. In 1600, Gilbert published a book known as De Magnete. This work was the culmination of at least 20 years of research. Robert Norman and Peter Peregrinus heavily influenced De Magnete, and the book also contained many of Gilbert's own investigations. He challenged popular myths about magnets, for instance, the long-held belief that diamonds weakened the power of lodestones. Before an audience, Gilbert tested the strength of the lodestone using 75 diamonds, demonstrating that they had no effect. Experiment played a key part in De Magnete. Throughout the book, Gilbert promises clearer proofs in the discovery of secrets being afforded by trustworthy experiments and demonstrated arguments. Many of Gilbert's ideas were idiosyncratic, yet he consistently supported them with empirical evidence. De Magnete began by exploring fundamental magnetic phenomena, starting with attraction. Gilbert avoided the term attraction, though, believing it implied a violent force, and preferred the term coition, which he thought described a gentle drawing together. This focus on attraction led him to downplay the role of repulsion, which he did not consider as fundamental. To support this, he noted that unmagnetized iron was always drawn to a lodestone, but never repelled. In another experiment, he floated 2 lodestones on water, and observed that while the repulsion weakly pushed them apart, attraction appeared to forcefully snap them together. It's difficult to determine whether Gilbert in fact believed that repulsion was a real effect at all. He sometimes implies that it's just a consequence of the attractive force. Gilbert also defined another type of motion, vorticity. This was the motion associated with the compass, where the magnet aligned itself north-south. In contrast to Norman, who thought the tip of the magnet was pulled north towards the point attractive, Gilbert imagined vorticity as a natural alignment. To investigate further, Gilbert followed Peter Peregrinus and performed experiments using terrella, pieces of lodestone shaped into spheres. Gilbert also created small compass-like devices, which he called versorium. Versorium contained small magnetized needles, pivoted to allow the needle to rotate. When placed on the terrella, the needles aligned and allowed Gilbert to observe the direction of the magnetic force at different points. This was almost a repeat of the experiment by Peter Peregrinus. But to Gilbert, it suggested something far greater than Peter had perceived. Gilbert realized that the Earth was a giant magnet. The Earth had poles just like the terrella, and when the terrella moved the versorium, it was exactly analogous to how the Earth affected the compass. Gilbert found further evidence of this bold idea. He noted that iron, left for an extended period of time in a north-south alignment, became magnetic. This would be the case, for example, in iron cast in buildings. Gilbert said that this observation is strange and incredible at first, but it made sense in the light of a magnetic Earth. The Earth was magnetizing the iron in the same way as the lodestone. Gilbert's discovery of the magnetic Earth was very great, but his eagerness also misled him, particularly in his investigation of declination. Working on reports from navigators, Gilbert knew declination varied irregularly. He hypothesized that declination was due to unevenness in the Earth's surface, so set out to build terrella which mimicked this. Gilbert had terrella crafted with huge hollowed-out seas and raised continents. When the Vesorium were placed across this surface, he found that the irregularities really did affect the direction of the needle. The observations, though, deceived Gilbert in thinking he had found the cause of declination. In reality, the uneven bumps he carved would have been enormous if they were scaled up to the size of the Earth. To all intents and purposes, the Earth is a sphere on a large scale, and irregularities in shape have a negligible effect on the compass. Elsewhere, his experiments with the terrella were more successful. Gilbert had read Norman's work on the point attractive and was aware of magnetic inclination. Since Norman, measurements had been made across the globe, and inclination was now known to vary by location. Gilbert suspected that inclination varied with latitude and set out to demonstrate this. He again used his terrella as a model for Earth, and this allowed him to investigate inclination without ever leaving London. The Vesorium were re-engineered so that the needle could rotate in the vertical plane. When placed at the pole of the terrella, the needle stood vertically, while at the equator, the Vesorium lay horizontally with respect to the surface. Gilbert marked lines of latitude along the surface of the terrella and found a position roughly equivalent to London's location on the globe. Remarkably, the needle dipped the exact amount found by Norman when he had measured inclination at London. Gilbert took this as confirmation that his terrella really were acting as microcosms of the entire world. Gilbert's inclination measurements undermined the idea that compass needles were drawn to the point attractive. Placing Vesorium across the globe, it was clear that the lines drawn from their axes did not converge at a single point. Gilbert saw that there may still be a relationship between latitude and inclination, but it wasn't a simple one. He collected a huge body of data and created complex geometrical diagrams to represent this connection. It was a partial success and allowed later construction of tables which linked inclination and latitude. Beyond the practical value of this work, Gilbert made many prescient speculations on the nature of magnetism. For Gilbert, inclination implied there must be something surrounding magnetic bodies which caused the needle to move. He called this the sphere of virtue, and it reached out past the physical body of the object. While the ancient Greeks abhorred the idea of action at a distance, in the early 17th century, a new generation were looking to break with the past. Gilbert saw no reason that magnetic effects couldn't reach out through space and affect other objects. De Magnete was a huge success on publication, and news of it spread widely. Unlike Norman, whose work was aimed at navigators, Gilbert's work was aimed at all those who were philosophically minded. Talk of the magnetic Earth even spread beyond the usual intellectual circles, and many popularizations of Gilbert's idea were produced. His discovery was clearly important and had a profound effect on many fields, perhaps most immediately on astronomy. Gilbert, like an increasing number of his contemporaries, was attracted to Copernicanism. While not a full believer, he at least subscribed to a weak version where the Earth rotated daily. Gilbert made a link between his own theory of magnetism and the daily rotation of the Earth. He suggested that the Earth possessed a magnetic soul that caused it to rotate. This, of course, was not a theory which had much legs, but another Copernican, a man called Johannes Kepler, read Der Magnete. Kepler was a true Copernican and the man who would revolutionize astronomy. Like Gilbert, Kepler had no problem with the idea of action at a distance, and when he needed to explain how the sun pulled along the planets, he appealed to the idea of magnetism. The remainder of this series will explore the progress made in astronomy in the late 16th and early 17th century. Until next time,